All right, we're going to move on. There's still maybe a couple topics for 3.6, but as I said, you have all the material that you need for 3.6. It's just learning to explore these applications. And so if I need to, I'll return to a couple of examples there. So I want to move on now to section 3.8. As a reminder, we already did 3.7. That was the chain rule. So we've already picked that one up. And we're moving on to 3.8 to learn the technique of implicit differentiation. And this is going to be a powerful technique for working with more complicated functions or more complicated even equations. So, let's take a look here. So if a function is in the form y equals f of x, then we're going to say that that function is in explicit form. Okay. Explicit form. An equation not in that form could still be thought of as an implicitly defined function of y in terms of the variable x. Okay, so we're going to introduce this vocabulary here: explicit functions versus implicit functions. Okay? So here I've got an equation, y equals 2/3 x minus 5. This explicitly defines y as a function of x. And it's for that reason, even though you had studied equations for a long time prior to learning function notation, that when you were given an equation in this form, then when you started talking about functions, they said, oh, just think of f of x as y. Well, that's not, I mean, there's more to a function than just saying f of x is the same as y. But if your equation was explicitly defining y as a function of x, then the two are interchangeable. Okay? But only when it's in that case. Okay? So in a different form, here I've got the exact same equation in a different form. Now, this is not an explicit function. Okay? Instead, it could be thought to implicitly define a function of y in terms of x. Now, in calling y the thing that's being defined in terms of x, we're making a choice here, and that choice is the common choice that we let x be the independent variable and y be the dependent variable. But technically, when it's in this implicit form, it's not clear who depends on whom. That's why I'm saying it could be thought of, as opposed to is an implicitly defined function. It just depends on your perspective. Okay? So in the previous example, I'm saying that 2x minus 3y implicitly defines y as a function of x. How could we put this into explicit form? We could do so simply by solving this equation for y. So we get, minus 3y equals negative 2x plus 15, or that y is equal to 2/3 x minus 5. And now you see that we have the same explicitly defined function that we had before. Okay. Why are we doing this? Well, in a minute here, we'll talk some more about some of the concrete benefits. But just to give you a heads up where we're going, we want to go ahead and take the derivative of an implicitly defined function. We're going to learn how to take the derivative of this when it's in implicit form as opposed to explicit form. And we'll see why that's beneficial here in just a minute. Okay, but that's where we're going. I want to take the derivative of this expression, this initial expression here, even though I already know how to take the derivative of its explicit form. Okay? All right, so let me give you some context for why we want to do this. Okay? This equation right here could be thought of as an implicitly defined function of y in terms of the variable x. Okay? When I go to try to put this into explicit form, I can't. I can't put this in explicit form of just a single function. Let's see what happens when we try to go ahead and solve it for y. We get x squared plus y squared equals 25. So that gives me y squared equals 25 minus x squared. And what's my next step in solving for y? Thomas, what do you want to do?
Well, to get rid of the square, you can take the square root.
Okay. So Thomas is saying take the square root of both sides. In practice, I don't disagree with that. I would like you to start kind of shifting away from the idea of taking the square root of both sides. You can't technically take the square root of both sides of an equation. Instead, what you're doing is you're applying the square root method, which looks like exactly what Thomas said. When you apply the square root method, you get 25 minus x squared, and we're going to put an x squared here. But what's the part that everyone forgets about when they apply the square root method? We got to have that plus or minus there. And for that reason, we're not taking the square root of both sides. We're applying the square root method. Okay? So what are our two functions? Our first function is y1 equals the square root of 25 minus x squared. And our second function is y2 equals negative square root of 25 minus x squared. Okay? Notice that this expression right here is not a function, not a let me just say not an explicit function. How come? Why is that not an explicit function?
Is it because it has multiple solutions for y?
Yeah, the definition of a function is for one given input. The definition of an explicit function is for one given input, there is one given output. But if I were to plug in, say, 0 for x, what are my outputs? Both 5 and negative 5. So that is not an explicitly defined function. In terms of vocabulary you've used before, it fails the vertical line test. That's okay. We can get around it, and that's what we're going to do from here on out. So I still want you to remember what denotes an explicit function, and it must pass the vertical line test. But now we can go ahead and say this is still a function. This expression right here is still a function, y given in terms of x. But I have to, if I want to give it an explicit form, I have to list two functions to describe it. Okay? By the way, what does the graph of this look like? What does the graph of y1 look like? Do you remember?
Semicircle?
The top half of a semicircle, or well, the top semicircle of a circle, right? Yeah, and the negative is the bottom semicircle, and put the two together, what do you have? The circle described by this implicitly defined function. Okay? We'll look at that graph here in just a second. So we can now easily take the derivatives of these two functions. We would say that y1 prime would be what? What's the derivative of y1? Yeah, 1 over 2 times the square root of that expression. Am I done?
No.
No, what do I need to do?
Chain rule.
The chain rule, which says take the derivative of what's inside that expression. What's the derivative of what's inside that expression? Yeah, I'll go ahead and write 0 minus 2x, just to remind you, because we haven't done a chain rule since Monday. Any questions on that? Okay. And so then what is y2 prime? It would be positive 2x. Oops, let's clean these up. I'm going to clean this first one up. This would give me a negative x in the numerator because the 2's cancel, so we'd have negative x over the square root of 25 minus x squared, right, when we go ahead and clean that up. And when we take the derivative of the second y2, in this case, we would just get positive x over the square root of 25 minus x squared. How come positive? Because we had a negative in the original function, and then when we did the chain rule, we'd introduce another negative, and the two would cancel out. Any questions on that, folks? Okay, so we've seen, should you want, if you're given an implicitly defined function, you could try to solve it explicitly for one or more explicitly defined functions, and then take the derivative of each explicitly defined function. Of course, that means you have to take multiple derivatives, right? Okay. But what we could see is that even though, so I would say that number 4 was easy to put into explicit form. Number 5, not too bad, but when we put it into explicit form, we had two separate functions. Okay? Number 7 here, this is called the full lemma of Descartes. We've got x cubed plus y cubed equals 6xy. Descartes, not Descartes, excuse me, volume of Descartes. When we put this, you could put this into explicit form. It would require, I believe, 3 separate functions to put it into explicit form, and it would be a lot of work to get it there. Okay? I'm not going to try. I couldn't do it. It would take me the rest of the afternoon to put this into explicit form. You could do it, but it'd be really tough. Okay? Further, I can give you other functions where it's impossible to put it into explicit form. It cannot be done. Nonetheless, I would still like to be able to take the derivatives of these functions, because all of these have graphs, and all of them then would have tangent lines, and on all of them I'd like to be able to talk about the slopes of the tangent lines. So I still want to take the derivative of these implicitly defined functions. The process of doing that is called implicit differentiation. All right. So let's kind of get to the heart of this. Suppose y is this function right here. Y is equal to x squared minus x. Okay? And then we've got this function right here. A of x is equal to x to the 5th power plus y x to the 7th plus hx cubed. Okay? If I went through to differentiate this termwise, let's see what happens. Okay? When I take the derivative of the first term, I get 5x to the 4th. Everyone agree? Okay. When I take the derivative of the last term, I'm taking the derivative of hx cubed. What happens to that h? It's a constant, right? And what happens with constants when you take the derivative? Everybody, they just come along for the ride. What happens when you take derivatives of constants? They come along for the ride. Okay? So what is the derivative of hx cubed? It's 3h x squared. Folks, are there any questions on that? Folks, this is supposed to be the clarifying example. This is the one that you should feel 100% comfortable with. I'm not getting much feedback from you. How do you feel about that? Give me thumbs up, thumbs down, thumbs sideways. Anyone want to talk about it anymore? Okay. Now, here's the mistake that people make. When I go to take the derivative of this, oops, excuse me, that should be yx to the 7th. Sorry about that. When I go to take the derivative of that middle term there, yx to the 7th, okay, well, shoot. It is not 7yx to the 6th. This is extremely important. And I'm sorry I've got those typos in there. When I go to take the derivative of yx to the 7th, it is not 7yx to the 6th. Curtis, why not?
Because they're multiplied by each other.
What do you mean? I think I agree.
Because you have to do a rule. Product rule.
Yeah, I think you're onto it. What factor you use? What information in the beginning of this problem are you using?
The derivative of y times x.
Okay, so here's the thing, folks. What was h in this? What was h in this function here? Constant. We just inferred that by its placement, by the letter choice we use. But what is y? Is y a constant? Y itself is another function of x, right? And so because y is also a function of x, I cannot treat it as a constant that just comes along for the ride. Okay? So instead, how would we take the derivative of yx to the 7th? Okay? Well, one way to do so is to do the substitution, because we know what y is, so let's actually do the substitution. That would be x squared minus x times x to the 7th. Right? And then as Curtis said, what type of rule are we going to have to do when we take the derivative of this expression? We're going to have to do a product rule on it. So when we go to take its derivative, here's the first times the derivative of the second plus the second times the derivative of the first. Okay. Which gives us x squared minus x times 7x to the 6th plus x to the 7th times 2x minus 1. Okay. Specifically, folks, there is the 7y to the 6th. There's the 7. This expression right here is the y, x to the 6th, that maybe somebody might accidentally think was the derivative of this, but they're missing this whole second piece of the product rule. Okay? All right, so I think we brought that home. All right. In the last example, we saw that, okay, if y is some function, then you cannot just bring the y along as a constant. Okay? And in this case, we were able to figure it out because we knew what y was. At the very beginning of this problem, I said, hey, y is this function right here. So then when we had to take the derivative of a term involving y, we just did a substitution step. But we may not be able to determine what y is, for reasons that I mentioned before. We might not be able to solve for y. But we can still do this derivative just as we did. So let's go ahead and do it again. So without knowing what y is, let's take the derivative of yx to the 7th. Without knowing what y is, the only thing we know is that it defines a function of x. Let's go ahead and take its derivative. Okay? So here we go. It'll be the first times the derivative of the second plus the second, which is, oops, sorry, I said first. I'm doing my product rule backwards. Here's the first times the derivative of the second plus the second times the derivative of the first, which cleans up to be 7x to the 6th times y plus x to the 7th times dy dx. And we've taken the derivative as far as we can without knowing what function y is. So this technique right here, this technique is called implicit differentiation. This idea right here is implicit differentiation. Okay. So let's put it into practice. Okay. By the way, this is a technique that I find confusing at first, and it's one that you just need to see we got to work a lot of examples. The more examples you work, the easier it gets very quickly. Okay? But I remember when I first learned this, I was feeling a little shaky right now. Okay? Let's go ahead and try this. We're given this curve. X squared plus y squared equals 25, right? This was the function from the previous side. On the previous page, how did we find its derivative? By solving for it explicitly first, and then taking the derivative of each of those two functions. Here we're going to find the derivative implicitly. So this is the steps that I want you to write out. Do write this first step out, folks. People try not to write this first step. They make all sorts of mistakes. So I've said, okay, fine. I need you to write this out, so I will dock you if you don't. Okay? What I'm about to do is take the derivative of both sides of the equation. Okay? Folks, what did I do between the question and this first line? What did I do?
Stated you're going to take the derivative of each side.
Right, I've just written out that I'm going to take the derivative of both sides of the equation. Everyone see that? Okay. So now let's go ahead and do so. Okay. I'm going to go ahead and input a chain rule where it doesn't necessarily belong. Okay, for this first piece right here. What is the derivative of x squared when taken with respect to x? What's the answer? 2x. Okay? The expression inside of the squared function is no more complicated than just an x, so I don't need a chain rule, right? But I'm going to go ahead and write it out anyway, just so you can see what's happening here. Okay? So here we go. The derivative of 2x, or the derivative of x squared would be 2x times the derivative of what was inside the x squared function. But what was inside the x squared function there? just an x. Okay? Let me write it like this. This might be more clear. Okay? Of course, what is dx, everyone? 1. So it doesn't make a difference whether I write it or not, right? Which is why we usually don't write it. Okay? Plus, what's the derivative of something squared? By the chain rule, it would be 2 times that something times the derivative of the expression that's inside there. Maybe this time through I'll try and do this similarly. So let me write ddx of the stuff that was inside the squared function. Okay? Of course, what's the derivative of the expression on the right-hand side? 0, because we're taking the derivative of a constant. Okay, let's clean this up. This gives us 2x times 1. Where's that times 1 coming from? What do you say, Max? Where'd that times 1 come from? So just line it up, 2x, and then where'd that 1 come from?
In front of like the derivative.
Yeah, what's the derivative of x? 1. Good. Okay. Plus 2y, and then I'm just going to leave this as dy dx. I don't know how to take y's derivative, but we'll call it dy dx. We don't know how to take its derivative, but we know its derivative exists. Okay? And we get equals 0. This part's really important, folks. What did I ask you to find in this problem? dy dx, right? Okay, give the smart aleck math question, answer to a math question. Where's dy dx? There it is, right? Remember, you guys probably seen, they make memes of that, right? Find x, and so he points to it and says, there's x, right? But that's literally what we're doing here. I'm asking you to find dy dx. We implicitly differentiated both sides of this equation, and we've got a dy dx expression. Now what should I do with that expression? I should solve for it. Okay? So this gives me 2x plus 2y dy dx equals 0. So that gives me 2y dy dx equals negative 2x. And who am I solving for? Who am I solving for here? dy dx. Okay, Angela, what am I going to do to solve for dy dx?
Move 2y to the negative 2x side.
Yeah, exactly. Let's divide that 2y over. And that gives us dy dx equals negative 2x over 2y, or dy dx equals negative x over y. Without ever explicitly solving for y, we still took the derivative of this function. Okay? Let's go ahead and find an equation to the line tangent to the curve. Well, let me show up. Let me make sure there's no questions on this. Okay? And there very well may be. You're probably not feeling comfortable with this yet because I've only done one example, and this takes about 10 examples to feel comfortable with. Okay? But the idea is we were asked to find the derivative of this function. So I simply said take the derivative of both, we were asked to find the derivative of this equation, right, with respect to x. So what did I do? I took the derivative of both sides of this equation. Okay, everybody, what did I do? What did I do for my first step?
The derivative of both sides.
Took the derivative of both sides. This is a new step. You hadn't done this before. Everybody, what did I do to both sides? Took the derivative. Did I write dy dx? What did I write? d dx, which is take the derivative of what's inside the brackets or what's inside the parentheses. Okay. Then here I took the derivative of the first term, which was 2x, and if I wanted to, I could put dx dx. But of course, what is dx dx? It's 1. But over here, when I take the derivative of y squared, it is 2y times dy dx by the chain rule. When you do this procedure, you will end up with an equation involving the thing you're trying to find. So in finding the derivative, you have to solve an equation, which we've not had to do before. So I simply solve this equation for dy dx. folks, it's important that you think of dy dx as a variable. And so we're solving for that variable dy dx. Okay. Now that we've got this, we can now ask all the same questions that we've asked before. For example, find an equation to the line tangent to this curve at the ordered pair 3, 4. Let's do so. Okay. So we're trying to find something that looks like this. So we're looking at y minus, I'm going to go ahead and write it as back to the y1 notation instead of the f of x notation. How come? Well, yeah, so we don't have the function f, right? We didn't give this as an explicit function, so I can't write f of a. Okay? So I'll just write y1 equals dy dx, and here I'm going to introduce some complicated looking notation. That's the derivative, right? Dy dx, that's the derivative. Then this bar, and I'm going to put 3, 4. Ooh, how do we interpret that? This says take the derivative, or use the derivative function and evaluate it where? When x is 3 and y is 4. Okay? So this bar is evaluated at. Okay? So dy dx evaluated at 3, 4. Everybody, let's read that together. Let's try again. Dy dx evaluated at 3, 4. All together? Dy dx evaluated at 3, 4. All right. Times x minus x1. Do you see that that's still the equation of the tangent line, just like it's always been? Okay. So, off to the side, what is dy dx evaluated at 3, 4? That should be a straight line. Evaluated at 3, 4. What is it? It would be negative 3/4. Why did I write it like that? Because the derivative is negative x over y. Negative x coordinate over y coordinate. Okay. So we're ready. We get y minus 4 is equal to negative 3/4 times x minus 3. Any questions about how we just found that equation of the tangent line? Okay, next page. Let's put this all together. Okay. The equation x squared plus y squared equals 25 defines a what?
Circle.
Circle with a centered where? At the origin, good, with radius 5. So here's the graph of this implicitly defined function. Okay? So folks, let's look at this picture right here. In earlier math classes, we would have looked at this graph right here and we would have said, is this the graph of a function? Really what we meant was, is this the graph of an explicitly defined function? And the answer was what? No, because if you want to describe this, you actually need 2 explicitly defined functions. Okay? But this is the graph of a function. Okay? If you tell me what x value, well, this is the graph of a function, an implicitly defined function. Okay? Now, when we did this explicitly, when we found the 2 semicircles, the first function gave us the upper semicircle. The second function gave us the lower semicircle. Okay? Okay. With a little bit of overlap that we're not going to worry about. Okay? Now, what were we just tasked with finding? We were just tasked with finding the equation of the tangent line at the ordered pair 3, 4. And we found that the equation of the tangent line was this line right here. Y minus 4 equals negative 3/4 x minus 3. That's what we just found. Now, there's one huge advantage to being able to do this implicit differentiation that I don't think we get when we do the explicit differentiation. And that is we can now talk about where we have vertical tangent lines in a much easier way without having to really use limits. Okay? So here I ask, where does this curve have horizontal and vertical tangent lines? Okay. Well, what was the derivative of this function? Negative x over y. Okay. By the way, that should remind you of something that if you've had a physics class and you've talked about centripetal forces, that negative x over y should sound a little familiar. Okay? That's the force that's always pulling you to the, that's the force that's pulling you to the center of that circle in a way. Okay? All right. If I want to figure out where we have horizontal tangent lines, what do I do? Nothing to do with today's lecture.
Set the derivative.
Yeah, if we want to find horizontal tangent lines, what do? You set the derivative equal to 0. Okay? When does that happen? When does negative x over y equal 0? It's a fraction, folks. When is a fraction equal to 0? When the numerator is 0. Okay. So now we go back to our function, our original function. We have x squared plus y squared equals 25. So let's plug in 0 for x. So it gives us 0 squared plus y squared equals 25. That happens when y is equal to plus or minus 5. So where do we have horizontal tangent lines? At the order pair 0, 5 and 0, negative 5. That's where we have horizontal tangent lines. Does that fit with the graph that we're looking at? Yeah. Go to 0, 5. Do we have a horizontal tangent line? Yes, indeed. Go to 0, negative 5. Do we have a horizontal tangent line? Yeah. How did we do that again? We set the derivative equal to 0 to find out where the slopes of the tangent lines were 0. How about vertical tangent lines? Where do we have vertical tangent lines? Well, we said before that what's the slope of a vertical line? No, not infinity per se. So in just an algebra class, we said what's the slope of a vertical line? We said that slope is, I heard it, undefined, where the slope is undefined, right? So we asked where is dy dx undefined? Well, dy dx is equal to negative x over y. Where is this undefined? When y equals 0. Go ahead and plug x squared plus 0 squared equals 25. We find that happens when x equals plus or minus 5. So where do we have vertical tangent lines? We have vertical tangent lines here at the order pairs negative 5, 0, and at the order pair 5, 0. How did we see that? We saw that by looking where the derivative was undefined. Okay. Now careful. Yep. Now careful, just because you get that the derivative is undefined there, there's technically some more checking that you have to do. That gives you the potential locations where you have vertical tangent lines. You could also have what? A corner there. Or just the function's discontinuous there. So you do have to actually do a little more checking that we're not going to worry about right now. Okay, we'll worry about that when we get to graphing in chapter 4. Okay. So that's where we had vertical tangent lines, right? Does everyone see it? Does everyone see your vertical tangent lines there? Okay. All right. So, in the time remaining, I want to get us as good as we can at implicit differentiation. This is the idea. There's no new material here, but let's practice this. And what I often find is if you start with a hard question, it makes a lot more sense when you get to the easier questions. So we're going to do the hardest question I can ask you, just about, for this implicit differentiation. Okay. I'm going to, since I'm running out of room here, let's put this on another page. Let's see here. hopefully you guys have that page in front of you, so hopefully you can see that. All right, I want to just find the derivative of this function. Okay. Do I want to try to solve this function for y? Try it, I dare you. Try it. You should. You won't be able to. Okay? So what should I do here? I should use this, since I can't explicitly solve it for y, I should use the technique of what, Daniel? That's all right, implicit differentiation. Okay. All right, so we take ddx of both sides. Okay, folks, I know that a lot of you are going to want to avoid writing this step. I require you to write it. I will mark you wrong if you don't write this step. I'm sorry, it's a little bit of extra writing. Okay? But you must write out this step. Does everyone see what I just did there? Darcy, how would you describe that step? What did we do? Yeah, so we're getting ready to implicitly differentiate, so we just take the derivative of both sides of an equation. Okay? Just like you might square both sides of an equation. We're taking the derivative of both sides. Okay? All right. I'm doing this. This is a long example. Okay? But hopefully it's going to clarify what's going on here. All right. We're taking the derivative with respect to what variable? X. So what is the derivative of 3x, folks? It is just 3. Nothing new. Okay? What is y? Y is some function involving x. I don't know what y is, right? Because I couldn't solve this for y. But what is y? It's some function involving x. What is the derivative of something, a constant times just a linear function? It's just the what? It's just the constant, but then we've got to multiply by the derivative of that large expression involving x, right? So I'm going to have a 3 and then a dy dx. Why didn't I have a dx dx here? Well, what is dx dx? 1, so I won't write that. Okay. Equals, okay, so over here, what's the derivative of x?
1.
It's 1. What is the derivative of y?
Dx.
We don't know because we don't know what y is, but let's give it a name. Let's call it dy dx. How we doing, folks? Okay. If you can do this problem, you're set. Okay. What is the derivative of something cubed? It's 3 times that something squared, right? So the derivative of 3, or the derivative of x cubed is 3x squared. And then there's a times dx dx, right? But what is dx dx? It's just 1. But what about this one? What is the derivative of y cubed? Everyone write out what the derivative of y cubed is. Max, what'd you get?
I got 3y squared.
Close, but no cigar.
3y squared times the derivative.
Times the derivative of y, because there's a what rule happening here? Chain rule. How do you see the chain rule? Y is some large expression involving x that I can't find. So there's a chain rule there, so we get a dy dx from the chain rule, which is why we had to cover the chain rule before we could cover this section. Okay. Now what do I have to do? I've got x to the 4th times y to the 7th. What type of rule am I going to have to use here? Product rule, right? That's no problem. Here's the first times the derivative of the second. 7y to the 6th times dy dx. Okay, that's for this product rule right here. Okay. So there's the first times the derivative of the second plus the what? Plus the second. y to the 7th. Do I have to put a dy dx there? No, because I'm just copying out the second term times the derivative of the first, 4x cubed. Folks, don't let your eyes glaze over. This is your quintessential example. If you can understand this example, and it may take some work, you can understand all of these problems. So again, this part right here was my product rule. All right, let's keep going. We're now taking the derivative of the tangent of y. Everyone write out the derivative of the tangent of y. Check with your neighbor.
Yeah, that's what it was wrong. Yeah, I rewrote it.
Mia, what did we get for the tangent of y's derivative?
Oh.
What did we get for the, yeah, that's right, that's right.
Secant squared of y times dy dx.
Folks, what do you say? How do you take the derivative of the tangent of an expression? It's the secant squared of that expression. But then there's a chain rule. So by the chain rule, we multiply by the derivative of what was inside the tangent, which is how we get a dy dx. Okay? All right, now we've got this last term. Okay? Now let's find the derivative of the tangent of 4y squared. This is getting about as complicated as it gets. Okay? What's the derivative of the tangent of an expression? It's the secant squared of that expression. But the expression inside there was more complicated than just an x, so we've got to take the derivative of what was inside there. What is the derivative of 4y squared? It would be 8y times dy dx. Okay? Folks, I'm not going to make you do it on this problem. What's my next step?
Isolate.
Yeah, our goal is to find y prime or dy dx, right? So our next step is to solve that for dy dx. It's a little bit messy, okay, but we're out of time. So we'll pick it up next time. Folks, you've got a chance to kind of get ahead of things here.